The moment distribution method can be very effective for analyzing indeterminate beams or rigid frames, especially if there are high degrees of indeterminacy. In this problem, we'll analyze an indeterminate beam using the moment distribution method. The key concepts we'll use are determining fixed end moments and applying moment distribution to predict moments inside a beam. And here's our indeterminate beam. It is pin supported at A and D, has a uniform distributed load, and sits on supports that will act as rollers at B and C. E and I are constant along the entire length of the beam, and we're going to determine the vertical support reactions. And here's the approach we'll follow. We'll start by generating an approximate answer . Because after performing our lengthy calculations using the moment distribution method, we want to be able to evaluate whether we have reasonable results or not. Then to start the moment distribution method, we'll need to calculate the stiffness of each member and calculate the distribution factors. We also need to get the fixed end moments . Then we'll be ready to apply the moment distribution method. Which will be an iterative approach. Once we've completed moment distribution, we'll be able to find the moments in the beam . With that information, we'll be able to use equilibrium equations to find the support reactions . Then we'll evaluate those results by comparing with our approximation. Step 1. Let's find approximate vertical reactions. And to do that, let's assume that distributed load goes to the nearest vertical support. We have 4 vertical supports in this case: AY, BY, CY, and DY. And if the distributed load goes to the nearest one, we have a 4-foot and 4-foot split here, 10-foot and 10-foot split here, and a 4-foot and 4-foot split here. So we'll predict AY should be about 3 kips per foot, the distributed load, 4 feet of which travels toward the reaction at A, or so we will assume, and we'll get 12 kips up. By will be approximately 3 kips per foot. We get 4 feet contribution from the AB side, 10 feet contribution from the BC side. Put those together, 42 kips. And from the symmetry of the problem, CY will have to be the same as BY. That's 42 kips. And DY will have to be the same as AY. So we make that prediction 12 kips. And so we'll come back to these numbers and use them to help evaluate our moment distribution results. Now to begin the moment distribution method. And to do that, we need to find the stiffness of each element of the beam. And we'll use that to find the distribution factors. So let's start with bending stiffness. The stiffness for the element doesn't depend on which end we're looking at, so the stiffness at the A end and the B end are the same, and they are 4EI over the length. In the case of member AB, it's 4EI over 8 feet. Then the middle member, member BC. Again, it's 4EI. This time the length is 20 feet. And the last element, or member of this indeterminate beam, member CD, we have 4EI, and its length is 8 feet. Now the distribution factors. Since A and D are both pinned ends, the distribution factor at A is 1, and the distribution factor at D is 1. That means that when we release node A, all of the moment, all of the unbalanced moment, comes back into the beam. And when we release D, all of it comes back into the beam. None of it is stored in the support, which makes sense because the support is a pin and should not carry moment. Now for node B, let's sum all of the beam stiffnesses, or element stiffnesses, coming together at that node. So we have the stiffness BA plus the stiffness BC. And that will be, as we see above, 4EI over 8 feet plus 4EI over 20 feet. If we choose least common denominator, convert the numerators, add them up, we get 14 EI over 20 feet is the total stiffness at node B. And then we'll use that in order to figure out the distribution factor to each of the members framing in at B. So for member BA, it's the stiffness of BA over the summation of all the stiffnesses meeting at B. And so that's 4EI over 8 feet divided by the 14EI over 20 feet. If we cancel the EI, multiply these out, we get 0.714. So when node B is released, most of the moment will distribute into member BA. Then our distribution factor going in the other direction, member BC from node B, is K for member BC over the sum of all the stiffnesses meeting at B, and that's 4EI over 20 feet divided by the 14EI over 20 feet. 20 feet cancel, the EI's cancel, and we get a 0.286. And then for node C, well, as we look, E and I is the same for every piece. CD is the same length as AB. So from symmetry, we could do the calculations out longhand. Or we can take advantage of seeing that the distribution factor going into member BC is going to be 0.286, and most of the unbalanced moment at node C when it's released will go into member CD, 0.714. Now we need the fixed end moments. And since every beam segment has applied load, every beam segment has a fixed end moment. And note that I've drawn them all clockwise. That's intentional so that we don't have any sign convention problems as we distribute moments. And so we pick one direction to be positive, and typically that is clockwise. This one is A, B. Now, we have 6 fixed end moments we need to calculate. To calculate these, we're going to use information provided on the inside back cover of our text. When you look, there's a large variety of situations shown, one of which is fixed on both ends and uniform distributed load on the beam. And that's the situation we have for each of the 3 beam segments. And so we'll see that the fixed end moment is omega L squared over 12. We need to be very careful that we pay attention to sign convention. The pictures all in the inside back cover of our text show the direction of the moment. We're going to consider only clockwise as positive. So at the left end of these beams, it'll be a negative omega L squared over 12. So that means that the fixed end moment AB will be a minus the 3 kips per linear foot times the 8 feet length squared over 12, which is a negative 16 foot kips, and clockwise would have been positive. Now at the other end of the beam, if we go back and look inside the back cover, we see that the moment at the right end is also omega L squared over 12, but this one positive. So we have a positive omega L squared over 12, which will give us a positive 16 foot kips. It is indeed clockwise. Fixed end moment for BC will therefore become a minus omega L squared over 12, where we still have the same uniform distributed load, but our length of the beam segment is 20 feet. We square that, and we get a minus 100 foot kips. Fixed end moment at the end, B end of member BC. At the other end, we know we'll get exactly the same magnitude, but reverse the sign, so we get a positive 100 foot kips. And member CD, get a minus omega L squared over 12, and we're back to the 8 foot length, so we have a minus 16 foot kips. And at the other end, DC, we have the positive value 16 foot kips. Great. Now it's time to begin moment distribution. I've put together a chart that we can fill in so that we can keep all of our numbers lined up, and I've input already the 4 joints or nodes to our indeterminate beam and the members coming and meeting at each of those nodes. We have a distribution factor at each of those, and for member AB at joint A, we found the distribution factor would be 1, likewise for D. And then for BA, we found 0.714, BC 0.286, and then it reverses but same magnitudes at node C. So let's input those distribution factors into our chart, our worksheet. I'll kind of nestle these two numbers close together because they both apply to joint B and will be how unbalanced moments distribute in node B. And 0.286 and 0.714. It's the mirror image because of the symmetry of the problem. And a 1. Now to go back and get our fixed end moments, which we had recorded here, minus 16 and plus 16, minus 100 and plus 100, a minus 16 and plus 16. Now starting at this point, everything I input into our worksheet will be in units of foot kips. And normally I write out units throughout the problem, but that would really make this worksheet pretty difficult to read. And since the units will be foot kips throughout the entire worksheet, I think we'll be okay. Now we begin the moment distribution process by releasing one of these clamped nodes and letting the unbalanced moment distribute to the elements joining there. And I'm going to just start at the left, and so I'll release node A. And over here I'll keep track of a negative unbalanced moment so that I can then use this quantity to distribute back to the various elements meeting at the node. So I have a minus, the minus 16 that exists at the node, so my negative unbalanced moment is a plus 16 foot kips. My distribution factor is 1, so I take the plus 16 times 1, and that's how much is distributed into member AB. If we take a look, now that it's been distributed, there is no unbalanced moment, so I'll put an underscore here. The node is in equilibrium at this point. But by releasing the node to let it rotate and distribute moment, we get a carryover. Some of that moment transfers to the other end of the element, in this case to the B end of the element, and half of it travels across, and so we have a carryover of 8 foot kips. And we clamp everything back down and move to a different node, so I'm going to release B minus my unbalanced moment, the 16 minus 100 plus 8, gives me a positive 76 foot kips as my negative unbalanced moment. So I take 76 times 0.714 and I obtain 54.3. That's how much of the negative unbalanced moment distributes back into member BA. I take the 76 times 0.286 and I get 21.7. That's how much of the negative unbalanced moment comes into member BC. Again, I'll draw an underscore because node B is now in equilibrium. And so I will clamp it back down, but when I rotate, or when I let node B rotate and these moments distributed, we got carryover to the other ends of the elements. And so half of those distributed moments carry over to the other ends. Half of 54.3 will round off to 27.2. Half of 21.7 will round off to 10.8. Now we move to another node. Let's release node C. We need to find the unbalanced moment and then reverse the sign. We have the 100 minus 16 plus 10.8. And with the reversed sign we get a minus 94.8. So I now take that quantity, multiply it by the distribution factor 0.268, and get a negative 27.1 foot kips. I take this quantity, multiply it by the distribution factor 7.714, and get a negative 67.7 foot kips. And if we add all these numbers together, we'll see that node C is now in equilibrium. And we clamp it back down, but we have carryover to the other ends of the members. And so half of 27.1, or negative 27.1, will round off to be negative 13.6, and this is our carryover. Half of the negative 67.7 will round off to negative 33.8 foot kips. And now we're ready to release a new node. So let's go out to D. We'll add up the unbalanced moment, then we'll reverse the sign. 16 minus the 33.8 gives us a positive 17.8 foot kips once we reverse the sign. My distribution factor is 1, so the entire 17.8 gets put back into member DC, which brings that node into equilibrium. We clamp it down, but there is carryover to the other end. Half of 17.8 is 8.9 foot kips. And that was our carryover. Now we're ready to release another node. I don't have to follow a set pattern as long as we continue until we get a sufficiently small quantity distributing at each node. Another way of looking at it as long as we have a sufficiently small unbalanced moment at every node. But as I look at the unbalanced moments, the largest one is at node A, so I'm going to go over to A and release it. And my unbalanced moment is 27.2 foot kips, so I have a negative 27.2 to distribute back, and my distribution factor is a +1, so I get the negative 27.2, which brings this node into equilibrium. We clamp it back down, but there is a carryover to the other end of member AB of negative 13.6 foot kips. Now node B has the largest unbalanced moment, so I'm going to move to it. And so we take the negative sign, we're going to add up the unbalanced moments. We have a negative 13.6 and a negative 13.6. We add those up, reverse the sign, we get a positive 27.2. We'll take that quantity and we'll distribute it according to 0.714 goes back into member BA, and 0.286 times the 27.2 stays or goes into member BC. That brings node B into equilibrium, but we have carryover to the other ends of the members. And so 9.7 carries over to the A end of member AB, and 3.9 carries over to the C end of member BC. Node C now has the largest unbalanced moment, so let's release C. We have a negative, we have the 3.9 and the 8.9. Now I'm not adding these up because I know they already add up to 0, but you could put them into your calculator just to check. When I add these up, put the negative sign out front, you get a negative 12.8 foot kips that must be distributed in order to bring node C back into equilibrium. So we take the negative 12.8 times the 0.286 distribution factor, and I get a negative 3.7 coming into member CB, and I take the negative 12.8 times the 0.714 distribution factor, and I get a negative 9.1 foot kips into member CB. And this brings node C into equilibrium, but we'll have carryover that I will continue on the next page. So our carryover leads into member BC, a negative 1.8 foot kips, and into member DC, a negative 4.6 foot kips. And even though it's not the largest unbalanced moment, since I'm here, I'm going to go ahead and release node D. My unbalanced moment is just the negative 4.6, because that node was in equilibrium on the previous page. And so we get a positive 4.6 foot kips to distribute back. Our distribution factor is 1, and so this node is now in equilibrium again, but we will have carryover back to the other end of the member, and so we get a 2.3 foot kips transferring to the C end of member CD. So now let's go to the largest unbalanced moment, which is at node A. So I look back on my previous page of this worksheet and see that our node was in equilibrium here, and then we received a positive 9.7, so this is the only unbalanced moment. So we have minus the 9.7, which gives us a minus 9.7 foot kips that we need to distribute at node A. The distribution factor is plus 1, so we have a minus 9.7, which then brings this node into equilibrium. We clamp it back down, and we have carryover to the other side. So to the B end of member AB, we receive a quantity we'll round off to be negative 4.8 foot kips. Now, our largest unbalanced moment is at node B. So let's release B. If we look back on the previous page of our worksheet, node B was in equilibrium by the time we'd filled that worksheet, so the only contributions to unbalanced moment are these two. The negative 4.8 and the negative 1.8 foot kips. When we reverse the sign, we get a positive 6.6 foot kips that must be distributed at node B. We'll take 0.714 as the component that gets distributed to member BA, and that's a positive 4.7 foot kips. The 0.286 times the M quantity we must distribute is a positive 1.9 foot kips, and that brings node B back into equilibrium. We clamp it down, but there is carryover moment to the other end when we let B rotate. And so to node A, end of member AB, we get a positive 2.4 once we round off, and to node node C, end of member BC, the carryover rounds off to a 1.0 foot kips. Now our biggest unbalanced moment is at node C. Take a negative, and our node was in equilibrium right before we changed worksheets, so only these two contribute to the unbalanced moment. So we have a minus 3.3 foot kips that we need to distribute. If we take that times our distribution factor of 0.286, it means that a negative 0.9 foot kips will come into member CB, and when we take this distribution factor times the quantity we need to balance, it means that there will be a negative 2.4 foot kips coming into member CD, and now node C is in equilibrium. We clamp it down, but there is carryover. And so into node D, we get a negative 1.2 foot kips. Into the B end of member BC, we carry over what will round off to be a negative 0.4 foot kips. Now, although it's not the largest unbalanced moment since we're here, let's go ahead and release node D so that we can bring that node into equilibrium. We have minus, it was in equilibrium here, so we have a minus 1.2. We need to 1.2. We need a positive 1.2 in order to keep this node in equilibrium. It's a plus 1 distribution factor. That brings node D into equilibrium. We clamp it back down, but not before we get a carryover of a positive 0.6. Now let's come back to node A, which has our largest unbalanced moment. The rest of our unbalanced moments are less than 1 foot kip. At some point, we have to decide to stop. Let's distribute the unbalanced moment at A, carry over, and then we'll decide if we're ready to finish. So I have a negative, only the 2.4, and so we need to distribute a negative 2.4 foot kips. Distribution factor is a full 1 because it is a pinned end. That brings node A into equilibrium, and we get a carryover of a negative 1.2 foot kips. Now we could continue on to a new worksheet on a new page, but at this point my peak unbalanced moment is about 1.5 foot kips, and remember my fixed end moments were 16 and 100 foot kips. So let's assume for a moment that we've distributed moments sufficiently well that the effects of the round-off error, or this truncation of the process, won't detrimentally affect our results. But we will do some things to check that as we generate our vertical support reactions. So we are ready for step 5. Find the moments inside the beam. And we do that by adding up within individual columns. So for joint A, we go to the top of our worksheet and we start adding up. Negative 16 plus 16 plus 27.2 minus 27.2 plus 9.7 minus 9.7 plus 2.4 minus 2.4. Add up the entire column and we get 0 foot kips, which is exactly what we would expect for a pinned end of a beam. So that quantity works out the way we expected. Now for the B end of member AB, we start plugging into our calculator 16 plus 8 plus 54.3 minus 13.6 plus 19.4 minus 4.8 plus 4.7 minus 1.2 equals a positive 82.8 foot kips. So I want to remind you this is all in units, foot kips. We go to the other side of node B. So member BC at node B. Again, we start inputting into our calculator negative 100 plus 21.7 minus 13.6 plus 7.8 minus 1.8 plus 1.9 minus 0.4, and that equals a negative 84.4. Now if we look at our sketch of the beam, you remember that we have two pieces of beam meeting at node B, no applied couple moment, no restraint on the rotation, so the moments should be identical in magnitude, opposite in sign at node B. In this case, their summation is about 0, but not exactly, and so that's due to round off. Right? Along the way we had to round off numbers, and we stopped the process here. So there is a little bit of a difference that is a sign of the iterative nature of the method. But let's keep going and we'll find out if this is a tolerable difference or not. So let's move to the other end of member BC, the end at node C. So we start calculating 100 plus 10.8 minus 27.1 plus 3.9 minus 3.7 plus 1.0 minus 0.9 All of that equals a positive 84.0. Now the other side of node C, member CD, and we begin calculating negative 16 minus 67.7 plus 8.9 minus 9.1 plus 2.3 minus 2.4 plus 0.6 all add to minus 83.4 foot kips. And again, when we add these up, we'd expect them to be exactly 0. They're approximately 0. The difference is due to round off and the truncation of our iterative process. But we'll find out if that's close enough. Last node, node D in member DC, we have 16 minus 33.8 plus 17.8 minus 4.6 plus 4.6 minus 1.2 plus 1.2. All of that adds to 0, as we would expect at the pin end of a beam. We now have sufficient information so that we can use the equations of equilibrium to find the vertical support reactions. Start with a free body diagram of element AB. It is 8 feet long, has the moment reaction at A, uniform distributed load of 3 kips per foot, unknown shear at B, and the moment MBA that we just calculated to be a positive 82.8. And that's in units foot kips. Now we sum moments, and let's sum them about point B. I can choose either direction to be positive for my summation. I'll pick clockwise since that's the direction we draw our moments. We get a positive contribution from AY, a negative contribution from the distributed load acting over 8 feet, that gives me the force resultant, acts at a distance of 8 feet over 2 from point B, and the moment at the cut, 82.8. We solve this for AY and we get a positive 1.6 kips up. And let's sum forces in the vertical direction. I'll choose up as positive. We have the 1.6 vertical reaction at A minus the 3 kip per foot uniform load acting over 8 feet minus the shear at B, or just to the left of B. And our unknown shear is a minus 22.4 kips. And we're looking at the left piece. If we had looked at the right piece, a positive shear would have been up. Now, free body diagram. Of member BC. This one is 20 feet long. Of a uniform distributed load of 3 kips per foot, a shear at the C end, an unknown shear at the B end, which is to the right side of B. I have my moment MBC, which we found to be negative 84.4 foot kips. And our moment at the C end, MCB, which we found to be a positive 84. So let's sum moments. Let's take them about point C. Again, I'll choose clockwise as positive. And so I get a positive contribution from the left moment, which is a negative 84.4. I get a positive contribution from the unknown shear just to the right of point B. A negative contribution from the distributed load, which acts over 20 feet to give me the resultant, and that resultant acts at 20 feet over 2 from point C. And then we have the moment at the right end, 84.0 foot kips. We solve this for the shear just to the right of point B, and we get a positive 30 kips. And again, it's our standard sign convention for internal shear. Now we'll sum forces in the vertical direction. We'll choose up to be positive. We have the shear just to the right of B minus the uniform distributed load acting over 20 feet minus the unknown shear just to the left of point C. We solve that for the unknown shear just to the left of point C and get a negative 30 kips with our standard sign convention for internal shear. Now, from the symmetry of the problem, we expect dy to equal ay. And we could just assume it to be so, or we can perform equilibrium on one more free body and let that be a check of our work so far. So we'll take a free body of member CD. It's 8 feet long. We have the unknown shear just to the right of D. The moment MCD that we calculated to be negative 83.4. Foot kips, the uniform distributed load, 3 kips per foot, and the vertical reaction dy. That's sum moments about point C. And again, I'll choose clockwise as positive since that's the way our moments are drawn. So I have a positive contribution but a negative magnitude for the moment CD. I have a positive contribution from the distributed load acting over 8 feet, the resultant acting 8 feet over 2 from point C, and a negative contribution from the reaction at D through 8 feet. Put those together and we get a dy as a positive 1.6 kips acting up, which does match what we calculated for AY. So that's a very good sign. So it's looking like the small differences in moments that we got from our moment distribution results are not going to play a significant role in the quality of our vertical reaction predictions. But let's continue. Let's draw a free body diagram of B. Just an infinitely short piece at B. So the distributed load doesn't matter because it acts over no length. We have the shear to the right of point B, which we found to be a positive 30 kips. The shear to the left of B, which we found to be a negative 22.4 kips. And we have our moments, which when we look at the node instead of the element, Newton's third law says the moments will be equal and opposite, and so they'll be drawn clockwise, or counterclockwise rather, but in this case I'm not going to input their values because it's irrelevant to my vertical equilibrium equation. I'll take up as positive, and so we have the negative 22.4 kips, the reaction at B, and the negative 30 kips. So By equals a positive 52.4 kips, and that's acting up. Now for Cy. In this case, since I have the other three vertical reactions, I could take a free body diagram of the entire beam. We see above that we calculated dy to be 1.6 kips. Remember that we said it matched AY exactly. We just saw that BY is 52.4 kips, and we're looking for CY. Can't forget the applied distributed load that got this all started. And this segment is 8 feet long, this segment is 20 feet long, and this segment is 8 feet long. We'll apply vertical equilibrium. Choose up to be positive. Get a positive contribution from the reaction at A, a positive contribution from the reaction at B, positive contribution from the reaction at C, and a positive contribution from the reaction at D. I get a negative contribution from the distributed load, which acts over a total of 36 feet. Add these all up, solve for CY, and I get a positive 52.4 kips, which is exactly the same as BY, which from the symmetry of this particular problem we would expect. And so now I'm ready to conclude that we did not stop our moment distribution process too soon, because our results demonstrate the symmetry that we expected. but I'm not yet quite ready to say that we have a reasonable result. To do that, I want to compare with our approximation. So if we go back and look, our approximate AY was 12 kips, BY and CY 42 kips, and DY 12 kips. All of which acting up. CY identical to BY, and DY identical to AY from the symmetry in this problem. And then from our moment distribution results, we found AY to be a positive 1.6 kips, acting up. We found BY to be 52.4, CY to be 52.4, and DY to be 1.6 kips, all acting up. Now, if we look at orders of magnitude, these all seem fine. When we look for the symmetry, due to the nature of the problem, these results look fine. But the magnitudes are a little bit farther away than I had initially expected. So let's take a look at the anticipated elastic curve for this beam. This is the longest span, and so we expect it to dip down. And if that's the case, this part will have to rise up. And so we've got a downward push that flattens this rise a little bit, but this is a really long span. And so if our elastic curve, our deflected shape, really did look like this, it would actually be reasonable to think that AY and DY might even need to be down. So the fact that it's small, smaller than our original prediction and close to zero, seems reasonable. So when we consider the elastic curve for our beam, the differences between our moment distribution results and our approximate results seem acceptable, and so we'll say we have reasonably predicted the vertical reactions of our indeterminate beam using moment distribution. Now let's go back and review the process we took to get here. We started by approximating the solution by assuming that the distributed load goes to the nearest vertical support. Then to begin the moment distribution process, we needed to find the bending stiffness for each element and the distribution factors at each of the nodes. We then calculated the fixed end moments using information from the inside back cover of our text. We created a worksheet where we input our distribution factors, fixed end moments, and then we began releasing the nodes one at a time, and as we reclamped each node, we calculated the carryover factor. We repeated the process until we felt like the unbalanced moment at each node was sufficiently small that we could stop. To find the moments inside the beam, we added up individual columns And we then use those internal moments to find the vertical support reactions, which we obtained and demonstrated symmetry, which we expect from this problem, even though we had some round-off error and some asymmetry or lack of symmetry in the internal moments based on when we stopped the moment distribution process. We then evaluated the reasonableness of our results by comparing the moment distribution results with our approximation. We then looked at the elastic curve to get some clues as to why the differences between the two, and concluded that we have a reasonable prediction from the moment distribution method. Well done.